which intersect in a single point. They're like smooth outside of this single point. We can consider, well, there are many examples. There could be lines which self-intersect, again, in one point. Does anyone remember equation for this? Something cubic. Well, I forgot. It's not hard. But on the other hand, there are some more bizarre things, like it could be a single line but without self-intersection, and it has like a beak in a point. Or other things. The only thing which unites all these examples is that they have smooth part and singular part. This was in dimension 1. In dimension 1, we have typically we have smooth part and finitely many singularities. If you remove them, you obtain something smooth, and then the singularities, you can study them separately. For bigger dimension, you can have something like, consider two equations, like P1 of x, y, z, gives smooth, so variety. We shall consider examples today. And then you have P2 of x, y, z, which is also smooth, in C3. This is complex dimension 2, smooth, so it's real dimension 4. Then you can consider the P1, P2 equals 0. It will be similar to that example, but the singular set will be equal to P1 equal P2 equals 0, because the points where these two varieties intersect are singular. And this is a curve, which could be again smooth or can have a point singularities. The total lesson which I wanted to give by this presentation is that you have a variety. It has smooth points, points where it looks like smooth manifold. Then the singular part outside of these smooth points, it has some singular variety of singular points, but it's also algebraic. We shall see that in the end of the course. It's also algebraic, and it also has smooth points and singular points. So you have like a smooth part. So you have x. X is a smooth part union with singular part. This is smooth. This is manifold. You can study it using topology and analysis. It's a nice thing. This is not very nice, but then this singular part can be also decomposed into smooth part. And its singular part. And so on. This is smooth. This can be decomposed again until the dimension, since each step the dimension decreases at least by 1, could be by 2. You can easily find examples where singular set is smaller, like dimension 0, for instance. But this ends definitely because the dimension decreases. Okay. This is one reason why we are interested in smooth manifolds. Another will be apparent later today. Good. Questions, comments? Now I will do something which is very elementary, and if you want me to give it fast or just skip, let me know. Okay, so first, what is topological manifold? A topological manifold is a topological space Do you know topological spaces? Who knows topological spaces? Good. You will need topological spaces because we need Zariski topology a lot. So topological space, please look in a book. It's something I could not introduce today, definitely. But what is important is that typical topological spaces look like, again, like that. This is what is called tree. You see there are different points. There are points where you have 3 branches together, and the points will have no branches. They are not homogeneous in the sense that the group of homomorphisms from a manifold, from a topological space to itself doesn't act on this tree homogeneously. On the other hand, if you have a circle, for instance, rotations act transitively on this space. You can prove that manifold has this property. So definition, topological manifold is a topological space locally homomorphic to a ball. So n-dimensional topological manifold. Okay, so the example is a circle, a sphere. You will see together there are lots of examples. Okay, this is a topological manifold. If you want to define smooth manifold or algebraic manifold, which we'll use a lot, it takes extra work. So essentially what you have an additional structure on top of the topological manifold structure. And there is, of course, it's a very simple notion, but there are still open questions, like this question of Busemann, characterize manifolds among other homogeneous topological spaces, still unknown. I mean, there's no way you can like ask all topological invariants to be the same as manifolds, and still it's unknown if it is really manifold or something. There could be other examples. Probably not, but it's still unknown. Okay. There's an exercise. Show that a group of homomorphism acts on a connected manifold transitively. Who of you can do that immediately? Okay, please.
Locally is for Rn. So locally we can find
a map from Rn to Rn, which maps a given point to a given point, right?
So we can do it.
How?
So if you have any 2 points.
Yeah, but how you can map any given point to any other given point?
I think you assume let it connect. So we have a curve, connect these 2 points, then you cover the curve by the open.
Well, the good answer is that you can take any map which takes point 1 to 0, and then you use the rotation to map any given x to 1 and other given y to 0. So what you need, in fact, is a map for which is a diffeomorphism which takes 0 to 1. And you can write it explicitly, or you can integrate a vector field. Okay, so we assume that you might know such a, and then
you just compromise all the maps F1.
well, the good answer, I think, is the following. You consider all points or the orbit of X under the diffeomorphism group. Now you use this result which you mentioned to prove that this orbit is open, because locally it's a ball, and in a ball you can move any point to any other point.
And the complement is
Yeah, and the complement is also open because it's another orbit. Okay, we won't use it, obviously. But it's really good to like feel the manifolds as geometric objects. We're doing geometry, and geometry is important. And you can always think of things like a sphere or a surface of a torus, things like that. Anyway, before I'm going further, I need to give you Banach fixed point theorem. It's I'm almost sure you know it, but let's do it. It's trivial. So you have a complete I mean, metric space is enough, but here it's Rn. So U inside Rn, closed. And then you have a map phi from U to itself, such that phi of x, distance from phi of x to phi of y, so it decreases distances, is less or equal than c, where c is less than 1, some constant, d of x to y. Then phi has a unique fixed point. So who knows this theorem already? Okay, you are very shy. The proof is, first, why unique? Because if you have two fixed points, the distance between them is, say, lambda, but then the distance between these images should be less than lambda because c is less than 1. Contradiction. Now, suppose you have any point, and I will consider a sequence. So x, phi of x, let's call it x0, let's call it x1, phi of x1 is x2, and so on. So the distance between xi and xi plus 1 is less or equal than the distance between x0 and x1 times c power I. Because how this, you have this interval from x0 to x1, you act on this interval, you obtain x1 to x2, but the distance is decreased by in c time, multiplied by c, then you do it again and again and again. So the sum of these distances, d from xi to xi plus 1, is bounded. So it's 1 over 1 minus c. Oh, sorry, from x0 to xi plus 1. This is a Cauchy sequence, in fact. Okay, Cauchy sequence has to converge, and it will converge to a point which is fixed. For trivial reason, because the sequence is mapped into itself by our transform. So this is a trivial but extremely important result. Yeah. There is a counterexample, it's for you. The funny thing that if you do try to do mathematics algorithmically, there is a part of mathematics which is called constructible analysis, where you do all estimates, it stops being true. So it really depends on in some sense, it depends on our understanding of math. But this is, of course, you can do unreasonable math without a Banach fixed point theorem, so we assume it. I mean, we assume the system of axioms where it is true. Okay. Now for differential maps. Well, everybody knows differential maps. It's just maps where all derivatives are, Rn to Rn where all derivatives exist, or you can define it like that. Define differential. Diffeomorphism is a map which is invertible, bijective invertible, and inverse map is also a differentiable. This chain rule. which in particular says that composition of smooth maps, differentiable maps, is smooth, and composition of diffeomorphism is diffeomorphism. I don't think I should spend time on that, but what is important is inverse function theorem. It's really nice result, which is much useful even in algebraic geometry. So we have a map phi theorem. You have a map. You can do it locally or globally on manifold. I will do it locally because locally it's true only locally anyway. So it's I mean you have so you have phi from U to V, where U V subsets in Rn containing 0. So 0 belongs to both, and then derivative, the d phi, it's a map from Rn to Rn. The tangent space to tangent space is invertible. Then phi is differ in a neighborhood of 0. So you probably know this. Who knows this already? You're not extremely happy. Well, I will give you the proof. It's a nice proof, and it entirely follows from Banach fixed point theorem. So proof. First, we can always take a composition with linear invertible map. I mean, if something is invertible, it remains invertible under a composition with fixed linear map, and if it is invertible, and vice versa. If it were invertible, it remains invertible. So taking a composition of phi with linear map. So this is an invertible linear map. I can even write which one. So it's d phi minus 1, the inverse of this. And I think I have minus. I want to have minus here. Right? Yeah. Then d phi becomes minus identity. It's enough to us to prove it in these assumptions. Then phi minus plus, is it plus or minus? Plus. Plus identity is less applied to this map, applied to some x is less than 1/2 of x absolute value for x sufficiently close to 0. This is because a differential phi minus identity plus identity is 0. If you have a map which has 0 differential, it's really like really small, around 0, by definition of derivative of a map. Okay. So we want to have inverse. This means that we want to solve an equation phi of x is equal c for a given c, right? So it was, well, need to solve. Okay, phi of x minus c plus x is equal c plus x. Plus, sorry, phi of e plus plus x is equal to c plus x. So where's, no, it should be, I'm doing something wrong here. No, I'm not. Yeah, so we're interested in fixed points of the map phi plus phi of x plus c, or minus c. So if it has fixed point, so it should be minus c. This means that phi of x plus x minus c is equal to x. And this means that phi of x is equal to c. Right? Simple arithmetics. Okay, but this map has to have fixed point because it's, I mean, c is small. This derivative of this map is 0. So the derivative of this whole map is 0. And it decreases distances. So it has fixed point, which is unique. And this fixed point is precisely, so you just solve this equation and you obtain the inverse map. To see that it is differentiable, you just, you notice that if you denote this map by phi, or psi for instance, then your fixed points is just iteration, limit of iterations of psi. So it's a fixed point. So solution is limit of psi, so this is psi n of x for any given x. It doesn't matter which, because it depends only on c. So let's call it phi c, for instance. Okay, the dependence on c is smooth, because you can just differentiate it under the limit. Okay. So this is slightly different proof, but it doesn't matter. It's yeah. Okay. Now, why are we interested in that? Because this theorem gives us, in particular, well, it gives lots of things, but one of the things which it gives is that it gives us a way of producing smooth manifolds. Yeah, so you can do it like formally, like it's in slides, or let me give you some informal way of doing it, and then we'll do it formally. So if you have phi from Rn to Rn, m is less or equal n, but the diffeomorphism, derivative of phi is surjective. Then you can make this map into a diffeomorphism by adding linear map. So let's take A from Rn to Rn minus m, such that d phi, direct sum with A, is a map from Rn to Rnm, direct sum with Rn minus m. Here I take the direct sum of two maps. Like on the first variable it is d phi, and the second it is A is invertible. This linear map. This is linear map. This is linear map. This is also linear map. And of course, if you have a surjective linear map, you can easily just add some identity. You have a matrix which is surjective. You just add something. You can always find such an A. You just take a kernel of this map and you take A, which is invertible on the kernel to this n minus m dimensional space. Okay, this means that phi plus A is locally diffeomorphism. Okay, and then you could take phi minus 1 of 0, which will be phi plus A minus 1, this preimage of 0. And then you apply that to 0 plus R n minus m. This is a submanifold, which is, this is invertible, so this is a submanifold which is diffeomorphic to, so it's equivalent to R n minus m. Because this is a preimage of R minus m. But this is the same as preimage of a point. This is the meaning of one of the applications of inverse function theorem, that if you take a preimage of a map which is called, of a value which is called regular value, I will explain why it is, then it is a smooth submanifold. In particular, if you have a function f, so example, you have a function f is a function from Rn to Rn to R1, for instance, just to R. And then you have df, which is a linear form. Suppose it's non-zero everywhere on U. So it's non-zero on U. Then f minus 1 of this of any C is a smooth hypersurface. Smooth hypersurface in the sense that was in last lecture, that it is a subset which is locally diffeomorphic to just a hyperplane. For example, you can take f equal to some xi squared, which is just absolute value squared. Then df is some xi d by dx xi dxi. This is a form which is non-zero outside of 0. So it's non-zero outside of 0, which is just 0, 0, a point with coordinate 0. Otherwise, it's non-zero, so f minus 1 of C is a smooth. This is sphere. This is how you prove that sphere is smooth. Because it's a level set of a function for which you can, you just consider f as one of the coordinates in a map which gives a diffeomorphism. Like here. Okay, now I will do more formally. So definition. So where this is standard and smooth topology. So f from Rn to Rm, or you can do with from manifold to manifold, except that we didn't define yet smooth manifold, is x inside Rn regular point if df restricted to x. So this is df is a map from Rn to Rm, which are just tangent spaces. So it's this is tangent space in x. This is tangent space in f of x. Surjective. And critical otherwise. Critical if it's not, so it's critical, x critical, if not regular. Okay, now definition, critical value. So again, we have f from Rn to Rm, smooth. X inside Rn. Rm, so sorry, y, because it's here. Rm, critical value, if y is an image f of a critical point. And regular, y regular value, otherwise. Okay, and as I explained to you in that presentation, preimage of a regular value is a submanifold. The important thing that there is a theorem of Sard, which is really like Sard lemma, but it's one of the most important statements in the whole smooth analysis. So theorem, critical values of any map have measure 0 and bare category as well. So most values are actually regular. So if you have a smooth map from Rn to Rm, any NMM, you have general point here, its preimage is a smooth submanifold, which I didn't define. Well, I did define it last time, but let's now give it as a definition. Oh, the definition is here. Yeah, so smooth submanifold is subset which can be mapped onto a coordinate hyperplane by a diffeomorphism. So definition, submanifold in Rn is M inside Rn, well, which is such that usually you also assume it is closed, but not always. Such that for all M inside this M, there exists diffeomorphism F from its neighborhood, Um neighborhood of M inside Rn. So I consider neighborhood not only in the smaller, but in the bigger. To say Rn, such that M restricted with is preimage F minus 1 of a linear subspace. This is one of the definitions of smooth manifold. In fact, it's the least useful one, but it gives you some geometric intuition. This is something which is locally. Of course, typically you consider smooth submanifolds, not smooth manifolds without any embedding. Embedding is additional data which you really don't want to have. Okay. So there is also this theorem that if you have a regular value, its preimage is a submanifold, and I sort of explained it. Maybe it's on the next. yeah, it's formal proof here. Okay. Since I already gave it, I would probably skip this slide unless you want me to focus on that. So is everything clear? So who has questions or just want me to be more slow? Who wants me to be more fast? Well, I can be more slow, but, well, do you want me? Okay, good. So let me prove this theorem. I gave you the definition of submanifold, right? Now I want to prove the following theorem. Well, the proof is already there, but we can spend some time trying to do it. Don't be shy. You can ask me lots of questions. I would appreciate it. So, a theorem. You have a smooth map. In fact, everything would work just as well for complex, for algebraic geometric setting. But I am giving that for Rn because Rn is more familiar. That's the only reason why I'm doing it with Rn. So you have a map F from Rn to, for Rn to n to Rm. And y is a regular value. Then f minus 1 of y is a smooth n minus m dimensional submanifold. Okay, so proof. Well, you need to prove it only locally. And so take by definition of a submanifold is something which is locally diffeomorphic to a subspace in Rn. So you take some m inside f minus 1 of y. Since this is a regular value, m is a regular point. So df restricted to m, this is a differential of the map f. So it's a map from Rn to R. M is surjective. Okay. And now we take, so we need only to construct a diffeomorphism of this neighborhood of this point such that our level set, f minus 1 of y, will be identified with a linear subspace. Okay, so we have this map. Let's call it A, or no, doesn't matter. So df restricted to m. Consider its kernel. Let's call it W. And W is, since this is surjective, the dimension of this is n, this is m, so W is n minus m. And I write map A from Rn minus m, from Rn to W, which any linear map will work as long as A restricted to W is isomorphism. So you would just take isomorphism, you would take a basis such that the first vectors are in W, and the rest of the vectors go anywhere, we don't care. So the important that it should be isomorphism. Such a map exists. And now we consider map F direct sum with A. So F is our original map, which is smooth, and A is linear. So this maps from Rn to Rm plus W. But since dimension of W is n minus m, this is the same as Rn. And the important thing about this map is that it has no kernel. Because if vector goes to 0, it already sits in W. Because F, kernel of F is W. But then A is invertible on W. It's actually isomorphism on W. So this is invertible map. Oh, df plus A is invertible. By construction. You can apply inverse function theorem and obtain that F plus A is diffeomorphism. And of course, now we finish the proof because F minus 1 of 0 is the same as F plus A minus 1 of 0 plus W. This is by definition. Okay. And this finishes the proof because we obtained that this F minus 1 of 0, oh, sorry, not of 0, of Y. So it's Y plus W, sorry. So preimage of Y is now a smooth subspace. I mean, it's diffeomorphism to a smooth subspace because this is a diffeomorphism and this is a preimage of Y plus, of the set Y, point Y plus W, where W is just, it's a fine subspace. Okay. So this is a way of constructing smooth submanifolds by taking regular values and their preimages. Do you have any questions, comments? Okay. Yeah. So if you have solutions of equations and their derivatives are linearly independent, the preimage, the solution, it's a preimage of 0, so it has smooth and dimensional submanifold. And then you have the same with regular value. I have already told you, so I would probably skip this, unless you have any questions. Okay, now we can have a definition of abstract manifolds, which is not something we shall use because if you go to algebraic geometry, this definition stops making sense very fast. But it's important for historical reasons and because most of the people who study manifolds study them from this point of view. So the idea is that, okay, so we just discussed submanifolds in Rn. But we are not interested in embedding to Rn. We are interested in submanifolds up to local diffeomorphism. So like up to a map which is like diffeomorphism everywhere and bijective. This is a very natural notion, of course. And so if it is embedded to Rn, to Rm, to R3, we don't care. Just we are not interested in embedding. We don't want to fix it. Because, I mean, this would, embedding it essentially means you fix coordinates, and we don't want. So if we do that abstractly, what you do, you consider a cover, so M, topological manifold. UI is a cover by open sets, so it is by open sets. So UI are subsets in M, and union of all UI is M. Okay, and each UI has a coordinate system. So each UI is embedded to Rn. It is equipped with embedding to Rn. So it's open embedding. Open means that in topological sense it's open, but you can identify it with an open ball if you like. So it can be just identified with an open ball. Bn open ball. I could write Rn instead of an open ball. This would be the same, but on the other hand, if you go to complex, then an open ball is not complex diffeomorphic to Cn. So it's better to be with consistent and do the open ball already. And then, okay, so this gives you coordinate charts. So this is charts. And this union is called atlas. So this union together with coordinates is called atlas. This is charts. And then you want to have, well, they will have to be consistent. So at each local set, they give you the smooth structure. This smooth structure should be compatible. So you have the map phi I. Let's call this phi I. Is it phi I here? Yeah. You have phi I from ui to ball. Then you have a map phi I multiplied by phi j minus 1. Well, you have two. Ui goes to an open ball and uj goes to an open ball. Of course, you can compare them only on the intersection subset. So it's a map from phi j of ui intersected with uj to phi I of ui intersected with uj. So this is transition maps. So this means that you have many balls with coordinates. Here you have two coordinate systems, and this is the map which compares these two coordinate systems. Should be smooth. And diffeomorphism. Okay. This is manifold. And then you have to, of course, now it becomes slightly more complicated because you have to, I mean, there's not, this is coordinate systems, but there are not a unique way of giving coordinate system on a manifold. You have to compare them. So you have to do equivalence of coordinate systems. This is on the next slide. Do you have any questions about that? Have you seen that? Who has seen that already? Okay, almost everybody. Very good, very good. So then now you probably know this as well, right? When the coordinate systems are equivalent. So coordinate systems are equivalent when you can have subdivide your two atlases by smaller atlases, and then these subdivisions would be the same. Well, I don't need that because I'm using different notion of manifolds anyway. Yeah, but what is probably, yeah, so this is, I defined your objects in the category of manifolds. This is morphism category of manifolds. This is maps between manifolds, which are smooth on coordinates. There's nothing tricky about that. Okay, now I will give you, but let's make a break, right? Make a break like 5 minutes, so it's now it's according to my clock it's 14:07. Let's meet in 14:12, and I will give you sheaves. This is really important, and we shall use sheaves. Like in algebraic geometry, you cannot do anything without sheaves. But today I will define smooth manifolds in terms of sheaves. It's fun. So you are free for 5 minutes. If you have questions, please ask. Feel free to ask me. So you can avoid using charts and atlases almost entirely. Okay, so what is, I want to give you the full definition of sheaf. We will use it at some point, but let's work with sheaf of functions now. It's enough for today's purpose. So definition, pre-sheaf of functions is on a topological space M is a collection of spaces F, let's call it F, F of U inside the space of all functions of U. So it's subspace. This is functions on U, and U is an open space, open subspace for all open subspaces. Okay, so what do we want about pre-sheaves? We need that for each U inside W, the restriction F of W restricted to U belongs to F of U. That's all. The typical example is continuous functions. So continuous functions are a pre-sheaf because you restrict continuous function on open subset, it remains continuous. Well, smooth functions are also a sheaf, as we shall, well, we didn't, well, yeah, we defined it. We defined already a manifold, we defined smooth map. So smooth functions are just functions which are smooth in all coordinate patches. And it is clear that if you restrict a smooth function on open subset, it remains smooth, because smoothness is a local property. So pre-sheaf is some set of functions which are defined locally. Now for the sheaves. For the sheaves, we need something else. We need more, because we want from local data to be able to pass to global data. So if we know our sheaf locally, we want to define it locally. So definition, pre-sheaf, a sheaf F on M is a pre-sheaf such that for all cover UI of U inside M open. So this is open, and UI, union of UI is equal to U. And for all collections, Fi inside, so this F of U is called the space of sections. So this is space of sections. So you have a collection of sections, Fi inside the F of Ui. On each open set, you have a small open set, you have a section like a function, such that Fi restricted to Ui intersected with Uj, so you restrict it to a smaller open subset, is equal to Fj restricted to the same, Ui intersected with Uj. So for such collection with this property, there exists, obviously unique, there exists F in F of U. So it's a section over U such that f restricted to ui is equal to fi. For instance, if you have a function which is locally smooth, it's globally smooth. If you have a function which is continuous on open sets, it's globally continuous. There are examples where it is not true on the next slide. Oh, I think I will skip that. You can see it later. We won't use it, at least for a long time. This is example of sheaves and pre-sheaves. Space of continuous functions is a sheaf. Smooth functions in differentiability class, like C1, C2, once differentiable, twice differentiable. Real analytic function, if you define real analytic manifold. But there are the pre-sheaves which are not sheaves. For instance, space of constant functions. Can you tell me why it is not a sheaf? Why it is pre-sheaf? You restrict constant function to a subset, it remains constant, clear. So the only axiom which doesn't hold is this one. So why it doesn't hold? Precisely, thank you very much. You have two sets, not connected. You put a function 1 on one set and 2 on the other set. They don't intersect, so this axiom is empty. There's nothing to compare. Intersection is 0. But obviously the glued section would be locally constant and not globally constant. So when you do a sheaf from constant functions, you would say locally constant functions, locally in each neighborhood. Now for bounded functions, can you tell me? Anyone? No, because you have two open sets, bounded in one, bounded in another. Precisely, thank you very much. So you do a similar thing. You take countably many open sets, and you do just constant, like 1 on the first set, 2 on the second set, 3 on the third set. They don't intersect. So you have to be able to glue this function to a global function, and it's not bounded because it's not bounded. Okay, good. Okay, now we want something else from our sheaves. We want it to be rings. So we extra, so definition, ring, sheaf of rings of functions is a sheaf f of M such that for each open subset in M, f of U is a ring closed under multiplication. And addition, of course, and addition. Now you can define ring space. Well, it's slightly bad definition because usually when you say ring space, you mean abstract sheaves, not sheaf of functions. And here I use, so it's a bad terminology. I'm sorry about this. At some point we'll have to redefine the terminology to have to be more general. But as long as you work over C, it doesn't matter. So definition, ring space is topological space with sheaf of functions. Now definition, morphism of ringed spaces is a map M1 to, say, M2, which is continuous. And second, for each open subset U inside M2, we take, let's call it phi, we take phi star of a functions which belong to f. Okay, so let's call it f2. Here we have the ring spaces, right? So they have m1, f1, m2, f2. We take preimage of functions which belong to f2 of u. And this should be inside f1 of preimage of u. This is very natural notion. I mean, for instance, we want to have smooth map. What we want about smooth map? We want that the preimage of the smooth function is smooth. Here we have all continuous. We want the preimage of continuous function to be continuous. So this is just abstract version of the same. I mean, I defined a category, but it's almost tautological. Yeah, so what is... of course, the example is smooth manifolds with of any class of smoothness. This is a ring space. The idea is that, okay, we don't like these atlases. We don't want them, and they don't really exist in algebraic geometry because everything is more intricate. So instead of that, we consider the smooth functions, and we use them to give a class of smoothness. So the idea that, okay, topological space is always the same, it's just our topological manifold, but the smooth structure is defined by these terrible atlases. So let's forget about atlases. We don't like them. Instead of them, we fix a class of smooth functions. It's enough, as you will see. Okay, so pullback of smooth is smooth. So natural, any smooth map of smooth manifolds gives you maps of ring spaces. The converse is also true, and this is slightly less trivial, but still trivial. So now claim. Suppose you have two smooth manifolds. There is a class Ci, but you can do C infinity, it doesn't matter. So M C infinity, N C infinity are smooth manifolds. Are ringed by smooth functions. So you have two sheaves of rings of smooth functions here and there. And now we can consider a map f from M to N morphism of ringed spaces. Then f is smooth. Okay, proof. Well, proof is essentially one line because you take f minus f star of coordinate function. Coordinate function is smooth. But this f star of coordinate function is precisely the form which f takes in coordinates. So if you have x1 on n, you have y1 dot yn coordinates on n locally. And then f on x, or on m, sorry, takes point m and maps it to, in these coordinates, to f star of y1, f star of yn. So this is f in coordinates y1 dot yn on n. This is by definition. So this is, so f of m is f, well, this is a tautology. So it is smooth, because in coordinates it's written as by these smooth functions. So what is f star of y1, for instance, applied to m? Is the same as y1 to f of m. This is first coordinate of f, and so on. So if all coordinates for your f, your right-hand coordinates, if all of them are smooth, this is smooth map. Coordinate is also true, but it is vacuous. So important thing is that the only data you have from manifolds is essentially smooth functions. There is no other data which you care about. So manifold is just a topological space, which is a manifold topologically, and a class of smooth functions given by a sheaf. This gives you a new definition, equivalent to the old one. And this is a good definition because this, unlike the definition with atlases, which makes no sense, this definition can be generalized to algebraic geometry. And we shall use it all the time. Okay, so definition. Algebraic, a smooth manifold is a ringed space M C infinity, which is locally means that such that for each, I will write that more explicitly, such that for each point M inside this big M, there exists a neighborhood. But this is local equivalence, of course. U containing this M such that U with this sheaf C infinity is isomorphic as a ringed space to an open ball. An open ball Bn inside Rn with a space C infinity of Bn smooth functions with the sheaf of smooth functions. Okay, so why this is equivalent to the usual definition, it's not hard to see because, okay, so now you can do it very like, so you have your usual definition with charts and atlases. So you take any chart which is a ball. Well, we can assume that our charts are balls. Then the smooth functions on this chart are like smooth functions on a ball. So it is definitely gives you this definition. Conversely, if you have a definition, smooth manifold that sets with sheaves and smooth functions, each of these open sets gives you a chart. I mean, by definition, it gives you a chart. Coordinates go to coordinates. But then you have to check that your transition maps are smooth. But then for transition maps, they give you just smooth functions on these intermediate open sets. So transition functions. So you have a chart U1 with coordinates U1 with coordinates x1 dot xn and u2 with coordinates y1 dot yn. So let's call it better v. Let's call this w. These are your coordinate functions. Now you have v intersected with w. Here you have two sets of functions, restriction of that and restriction of this. And you have to prove that they're transition functions, so you can express this. So this is smooth, need that xi are smooth expressions of ui and vice versa. Okay, now let's go back to this definition with smooth functions. They are both all smooth functions, right? By definition, because as you restrict to subset, they remain smooth. So if they are smooth in that coordinates as well, because it doesn't matter which coordinate we choose. You just removed we forget about coordinates, that's all. So the sheaves in that setup are just a way of forgetting about coordinates. Okay. Let me conclude with, today we had three definitions of smooth manifolds. Let me erase this, for instance. First is atlases and charts. Second is submanifolds. Third is sheaves. So I proved you equivalence between these two. Now, if you have a smooth submanifold, you can restrict smooth functions from ambient manifold to this submanifold. And since locally it's a product, you can do opposite. You can so it's if M is submanifold in Rn, locally M is just isomorphic to Rm inside Rn. This is an affine subspace. And then you can start with smooth functions on there, just extend it trivially in all directions. So you just take a function here and extend it into other coordinates that it doesn't depend on other coordinates. So it doesn't depend on embedding, and it gives you really smooth. Locally, this thing is isomorphic to an open ball, and you can restrict smooth functions from the outside, or you can just consider them on an open ball. It doesn't matter. So it's sort of clear that if you have a submanifold, this gives you a manifold with smooth functions by restriction, and also it gives you atlases and charts because you can have, this gives you charts. It's slightly more tricky to check, but it's not hard. In fact, the converse is also true, and you can embed any manifold to Rn. I'm not going to use that, of course, because it doesn't make sense in context of algebraic geometry, but it's a theorem of Whitney. Every smooth manifold. Well, I want to, which is Hausdorff. We didn't yet demanded that to be Hausdorff, so now we should. And then there is another notion which is called paracompact, which is really bizarre, but instead we can ask for that to be metrizable, to admit a metric. This equivalent to paracompact, and in fact, people historically they say paracompact just for stupid reasons. Just metrizable is good enough. So every submanifold, which is Hausdorff and metrizable, can be embedded to Rn. And connect, well, countably many connected components. So this gives you equivalence of all three definitions. Now for I'm not going to give you the proof because there's only 3 minutes. But you can ask me sometime, or I will give you. Well, it's not relevant for our course, so I'm not giving you that. And next time I will give you a couple of words about smooth manifolds, and then we shall go to the Noetherian rings and irreducible decomposition, this kind of stuff.
Part of arguments you're not concerned about the regular submanifold.
You mean this? Yeah. Well, just submanifold. It should be closed, closely embedded, smooth and closely embedded. Yeah.
I didn't quite understand this argument.
Which arrow you didn't understand?
I mean, locally the submanifold is equal to Rm, and
This is a definition, yes.
the definition, so this is like regular submanifold.
No, in my case, it was a definition of a submanifold. I don't know what is regular and irregular. I just don't quite understand your terminology. What is, in your case, is irregular?
Regular is that you can like be the first m parameters to parameters.
Yes, and what is not regular? What is not regular? You said that it is regular and there's some irregular, not regular stuff. What is it?
I'm not sure there is this, but I mean, in my book, this is a regular manifold.
Yeah, but what is non-regular?
I don't have a color example for that.
Okay, so they just use different terminology for the same notion, and there's no more general notion, I suppose, right? Okay, no, this is, it's always called submanifold, so you shouldn't be that careful about, because it's a submanifold. Of course, not every submanifold is closed. This is important. For instance, what you can do, you can take a sphere and then take its just half. So you take the set of all points x1 dot xn in a sphere such that x1 is bigger than 0. You cut the bottom half. This is not closed. It is locally a submanifold, but it is not a closed submanifold. This is important, and really from these boundary points, you can have lots of trouble. So people usually assume submanifolds are closed. This is one thing. Another thing is even worse, which is submanifold. Well, another thing is not submanifold in my definition, but it is a submanifold in some definition, which is the following. You take a torus, R2 by Z2. Irregular, usual torus, and then you take a line, L in Rn, which is the line of form T and alpha T, where alpha is irrational. And you can put it on a torus. It gives you, it will go infinitely around the torus, and it will be dense. So locally, it's really a line. It's locally, it's a manifold, but globally, it's dense. It's not a submanifold. It's not submanifold in my definition, but there are definitions where it is submanifold. Maybe this is what they wanted. So you can have local parameterization of this line, but in fact, as it goes, sorry, in R2, it goes around the torus densely, and it's infinite packing, infinite, how it is called? Infinite, well, it has a name. Okay, more questions, comments? Okay, and I gave the assignments. Some of you probably didn't have it, but you can have it easily here, and I hope that next time with your monitor you have to solve that, and you will discuss that with, oh no, you don't. Well, anyway, there is a third assignment. It should be there, but for some reason it's I don't know, I mistyped something. So there's a third assignment about divisibility. You're supposed to read it and try to solve. It should be trivial. Oh, no, it's there. Good. It's just not on the index. Yeah. Okay, you're free. Thank you very much.